Okay. When we think of circuits, what we're talking about is a path that electricity follows, and that electricity gets used for something. Okay? So there's some symbols here that you have to understand and know when you're building a circuit. Now, the PhET simulation that we went over in class, building a circuit, had actual pictures of things. But in real life, when you're putting together a circuit, you actually have to use symbols. So I don't know if you've ever seen, sometimes a repairman can look up the electrical diagram, is what it's called, of a television or a circuit board, and it has all these symbols. So I just want to talk about a few of these symbols with you. Okay, the first symbol is going to be that for some kind of cell. What do I mean by cell? Is like a battery. So it could be a car battery, it could be a AA, AAA, C battery, etc. So a single cell looks something like this, where you have a longer side and a shorter side, and there's a little gap between them. This is known as a cell, and it represents your power to your circuit. Now, if you have something that has two cells, then it would look something like this. Okay, and so this would be kind of like a double cell.
Are they the same length?
They are not. Well, the longer ones are the same length and the shorter ones are the same length. But there's meant to be a long one and a short one. The long ones represent positive and the short ones represent negative. A car battery is a 6-cell battery. So a car battery would be something like this. 2, 3, 4, 5, 6. It has lots of mini batteries inside of it. That's what gives it its 12-volt charge. Okay? Now, typically speaking, when we draw a cell in a circuit, we put how much power that cell can deliver above it. So if I saw a cell in a circuit, I might put like 9 volts above it like that. So that would be a representation of a 9-volt battery. Or if I put 1.5 volts above it, that'd be the representation of a AA or AAA or C or D battery. Okay, so go ahead and write that down. Any questions up to this point? Jaden?
If they deliver like around the same voltage, then why does there have to be separate battery sizes?
Anyone want to try to answer that? Have I talked about that before?
No.
Why are there separate battery sizes? It's actually less scientific and more historical. So if I'm saying it has to do with history, what do you think? Why do we have AAAs and AAs and C and D batteries if they all have the same voltage? Yeah.
Because it's about how much comes out of the atomic.
Possibly. I want you to think about, where do we mostly use batteries? Where have batteries mostly been used? Yeah.
In cars and some of your electronics.
Okay, electronics, sure. I have a little one at home. What do you think a lot of her toys run on? Yeah. Batteries. Toys. Toys for a long time have run on batteries, right? All right, so what have happened to toys and electronics, let's say from the 70s till now? Parker?
They've gotten a lot smaller.
They've gotten a lot smaller. And if you have smaller electronics, you need to have smaller batteries to power those electronics. Now, I mean, if I look at a remote like this is a remote. Remotes like that are more powerful than that. Okay? This is old school. This, new school. This is really thin. This is a fat behemoth. Okay? And so we have these big, used to have these big remotes. This remote takes AA. This remote, okay, takes a CR2025. Believe it or not, the CR2025 is a 3-volt battery. There are two AA's in this remote, this big one, that also are 3 volts. These two remotes are powered by the same voltage. But what has happened over time? The electronics have gone from being large to small. We are now able to build a lot smaller electronics. And so that's why a lot of our batteries have gotten smaller. Now, babies. Hang on one second. Babies still need toys that are large and bulky so that they don't swallow them, so that they have big, colorful, attractive things that they can play with their hands. And so yeah, we still actually use a lot. C batteries are very common in baby toys still. The older you get, the more you'll find that your electronics will take AA, AAA, a lot of flashlights now that are a lot smaller take AA, AAA, or they'll take something like a CR2025 or the CR2035, which are 3 volt batteries. Okay, Emma.
So is this why, like, when you look at iPhones, the iPhones are getting smaller and smaller because they can make
Cell phones have actually gone through. Cell phones have actually thinner. Exactly. Cell phones have gone through a unique phase in the sense that they got smaller and smaller and smaller, and they've actually reversed, and now we're starting to get bigger and bigger and bigger. Cell phones actually in the last couple of years have gotten bigger, but if we're talking screen size, but you are absolutely correct, Emma, in stating that they are getting thinner. And so actually every cell phone has a unique battery that's custom designed for it. There's a new iPhone being released. It's the iPhone 6C probably in April, and it's going to be smaller than the iPhone 6 and 6S or the iPhone 7 and 7S when those are released. And it's going to have even a larger battery yet in it. Okay, it's going to look a lot like the old iPhone 5. Yeah.
Wait, how many volts do the phone usually work on?
They do them in milliamp hours is how they don't actually give a voltage rating for those. And the reason is that because all of those batteries are what's different about a standard AA versus the batteries that are in phones these days, Colby? They're rechargeable. And so rechargeable batteries, we don't necessarily worry about their voltage output. We only really worry about how long do they last before they need a charge. And so it's now milliamp hours. It tells us how long basically the battery can go before it needs to be recharged.
Wasn't the smaller the battery that you would think the life is?
Possibly, sure.
So
Yep.
Like, if they're getting thinner, wouldn't the life go smaller?
But the technology is getting better. The electronics are getting smaller, which is making more space for the battery to take up inside the device. But I don't want to get too far off topic here, but that was a great question, Jaden. Basically what's happened is over time, historically, electronics are getting smaller, and so we've had to make smaller and smaller batteries. Okay? All right, so these are how we represent power in a circuit. Now, if we wanted to put a light bulb in a circuit, we oftentimes put a wire coming in to a circle, and in that circle we put a little like curly Q and then a thing out. That is basically what we call a bulb. Now, this type of bulb is very specific. It's an incandescent. Okay, and I probably spelled incandescent wrong because I'm not a very good speller, mind you. But it's an incandescent. What is an incandescent light bulb versus some of the others that are out there today? Parker?
Are they more efficient?
They not are more efficient. Think about like the different types of light bulbs you can buy at the store. What's an incandescent one? Yeah.
They're brighter and they last longer.
They are not. Think about the different shaped light bulbs.
Oh, these
Okay.
are like the curly cube ones.
Incandescent light bulbs are not the curly Q ones. They're the old school light bulbs. The ones that actually look like light bulbs. An incandescent light bulb is the kind that kind of comes down and then it's like this. And we,
Those are the ugly kind.
okay?
Really? You're hurting an alter ego.
Okay. What is another type of light bulb that we have in circuits these days? What's another type of light bulb? Yeah. LED. An LED symbol looks like this. Okay, this is, and it has an arrow here and an arrow here. This is an LED bulb. So if you're talking about powering an LED in a circuit, this is what you would put as a symbol. Okay. Now, as far as, hang on one second. Sometimes we have things that use electricity, but they're not light bulbs. So for instance, there's things called resistors, which use electricity. Certain light switches are types of resistors. Okay, so when we draw a switch, especially like a standard, what we call brake switch, it looks something like this. This is an open switch. This is a closed switch, and this right here is called a resistor. These are all different types of symbols when you are talking about building a circuit. Parker.
What does LED, like what's the stand name for? What does LED mean?
Light emitting diode.
But I always knew it from LED, but light emitting diode. What's diode?
Hang on.
Colby? Did I ask you?
Whoa, easy does it. Light emitting diode. Diodes are an electrical component. LEDs, believe it or not, have been around for a while. They, however, have not been in like headlights, household homes for a while because the technology to convert them over has taken some time to develop. For instance, now you can buy LEDs, especially Christmas lights, that are like red and green and blue, etc. Believe it or not, the blue LED took a very long time to develop. Okay, and so the technology has had to we've had to kind of allow the technology to develop before we've been able to make it for us. Okay, now LEDs are very common. They still are, however, expensive because the technology is still working. It's still somewhat new by most
The
standards.
cars that have it in them are a little more expensive.
Right, a lot of the cars that have LED headlights, LED brake lights, LED dashboards, things like that are a little bit more expensive. Okay, now that you have all of your symbols written down, let's go ahead and talk about building a regular circuit. Okay, so I'm going to go ahead and switch pages here. A little bit. It bled through a little bit. If you have about a half a page, you're going to be good so far. If you don't, go ahead and flip the page.
Like this much?
Yeah, that'd be fine.
Is that much?
Okay, what we are going to do is we are going to make what's called a series circuit. A series circuit. There are two types of circuits, series circuits and parallel circuits, okay? Series circuits are the kind that you're probably the most common with. It's a loop that's got some things in it, and when you connect the switch, it turns a light bulb on. So I'm going to draw a simple series circuit, okay? So the first thing you always draw is a cell. Let's just pretend like we're using a D battery. So I'm going to go ahead and I'm going to make it 1.5 volts. We're going to actually draw circuits like the ones you could actually make in class. So we won't be using LEDs in our symbols here because we don't have LED lights in class that we can use. Okay? We did have motors, but we're not going to get into the symbols for those. So right now we're basically just going to be working with incandescent light bulbs, also known as lamps, batteries, and switches. All right. Now, I'm going to go ahead and switch colors real quick.
Me too.
I'm going to draw all my wires in red.
Me too.
Okay. I'm going to go ahead and draw a switch here. And I'm going to make it open. And there's my light bulb. This is what we call a simple circuit. A simple series circuit. All right, when you think of like the World Series or a series of events, what are we talking about? Are all the games played at once in the World Series? No, you play game 1 and then what?
You play game 2.
And then you play game 2. And then you play game 3. And it usually, depending on how it goes, you play game 4, 5, 6, and sometimes a 7. Okay, so you have to win what? How many games to win the World Series? Yeah.
Is it 3 or 4?
You have to win 4 games. Basically, you have to win, I mean, of course, there's only 7 games, so if the other team can win 3 and you win 4, you win, okay? So the first team basically to win 4 games wins the World Series. Now, when we're talking about a series circuit, the word series means one after another, okay? So you will always basically see a simple loop. Okay, I'm going to call this the loop. Where you have something here, okay, I'm going to call this spot 1, and the electricity goes to spot 2, and then it goes around to spot 3, and then it returns. It goes around in a very specific order. There's no forks in the road, there's no detours, they have one path. Okay, so one path. That's very important. Now, if the switch is open, is there electricity flowing through this circuit? No, there's not. In order for this circuit to be powered, that switch has to be closed. So if I open the switch, everything turns off. If I close it, everything is on. So it's all or nothing. So that's the other thing I want you to understand about series circuits. It's all or nothing. All right? I think for the most part, this makes sense. Okay? I think for the most part. But before I move on to the next type of circuit, does anyone have any questions about this?
Can you give me like a minute?
Yeah, go ahead. If I did not have my lamp here, okay, or my light bulb, then I would have nothing that's using the electricity. What happens when you don't have something in your circuit that's using electricity? We call that what type of circuit? Parker?
Closed.
It will be closed, that's true, but it's a special type of circuit, one that's bad. It's one of the reasons we have circuit breakers in our house. Anybody?
Circuit breakers.
No? Savannah?
Broken circuit?
Not a broken circuit. That's a great guess. Yeah?
Short circuit.
A short circuit. All right, so if you don't have something, okay, by something I mean a light or motor or resistor to use or slow down the current, you have a short circuit. All right, I'm going to explain this kind of quickly, and I just want to kind of make sense. Everything that uses electricity slows down the traffic of the electricity. So think about the electricity as traffic on a highway, okay? Everything that you put in that circuit that's going to use up that traffic is kind of like stoplights or speed limit signs, okay? But if you don't have something there to slow the electricity down, the electricity current gets faster and faster and faster, and it starts delivering more electricity in greater quantities. Think about a faucet that can turn on and then turn on some more and then turn on some more, and eventually you have this huge gushing flow. Well, if the wires can't handle the flow because they're too small, what happens to the wires? They start to get hot because there's too much electricity current flowing through those wires. And if those wires get hot, they can potentially do what? Melt, spark, catch things on fire. So we put lamps, circuits, we put motors in circuits, we put resistors. Basically, we put something in the circuit to use up that electricity to keep the current down. Okay? If we pull too much electricity through that circuit, it can potentially be very, very dangerous. So one of the things that you always have to have if you have power in a circuit, and you wouldn't have a circuit without that, is you have to have something that's going to use that electricity, okay? So you have to have something providing the electricity, and you have to have something using the electricity. Switches are optional. But this, something like a light bulb or a motor or a resistor or a computer or something has to use electricity. Otherwise, you're in bad shape. Parker.
And when you said you have a breaker, but can't your breaker go off if you have too many things on one circuit?
When you have too many things on one circuit, it's drawing too much current through the wires. And then your breaker goes, ah, that's dangerous, oh my gosh, oh, turn it off. And then the breaker goes, whew, job done.
Well,
You go out there, you flip it.
Then you flip it, and then if you didn't make any changes, the breaker goes, ah, and flips it off.
They screwed up.
And it keeps clicking off until you adjust how much current you're drawing through that circuit. Okay? So those circuit breakers in your basement or closet or garage or wherever your breaker box is, they're designed to let a specific amount of current go through, and that current is tied to the size of the wire that's in your walls. Okay? So the whole system is deemed safe when they build the house. And then your breakers are there to make sure that you don't exceed the safe limit of electricity passing through those wires. Otherwise, bad news bears.
How's the breaker now?
Okay? Jackson.
And like my man cave, we have.
Oh, you have a man cave.
Yeah.
For who?
I thought it'd be
Me.
Don't you think that's false advertising?
No.
Okay.
It's a lizard cave back.
No, I'm kidding. No, really, you have a man cave. That's very cool. But I need to get on. We'll get back to this in just a minute.
Circuit and stuff, because I have too much stuff down there. In my
Do you?
basement to turn off.
I blow breakers all the time. The problem in my house is that every outlet on my main floor is on one circuit.
And I was also charging.
So, in houses back in the day, you didn't draw that much electricity, so they didn't worry so much about having multiple breakers. My house is old. Shh. All right. Ladies and gentlemen, one more type of circuit. And you really, for my purposes, you just need to be able to identify which one is series and which one is parallel. Okay? This is called a parallel circuit.
Your hands are hairy.
They are.
I think we're going down.
I just noticed. It looks like he shaved his hand.
Okay. Whereas in the last one, we said one path. This is what we call a multi-path circuit. Okay, so I'm going to go ahead and start drawing this. You obviously are going to have also, you have to have a power supply, and so I'm going to go 1.5 volts, so it'd be like a D battery. If this was a household power, you would have 120 volts there. Okay, all right, so we have the 1.5 volts, and again, I have my wires. So the wires come off the battery or the cell, and then something happens. They have a choice to make. In a parallel circuit, they split up. So in a parallel circuit, one might go this way, and then another one might keep going. And then it eventually branches off in this direction too. Okay? Now, on these little branches, I'm going to put one open switch, and down here I'm going to put a closed switch. I'm going to continue the circuit over a little bit, and then I'm going to draw a lamp. I'm going to draw another lamp. And then I'm going to connect everything back. So I'm going to come off this guy, and this one, and down, and over. This is called a parallel because both branches of the circuit are parallel. They run next to each other. Okay. All right. Now, I drew this very specifically for a reason. So I want you to kind of follow what I'm about to show you. I'm going to draw my electricity in green here. And let's just say the electricity comes out of this end, comes down, and then gets to my fork in the road. What do you think it does? Does it only choose one path? It splits. It says, "Hey, Giorgio, I'll go this way. Fabio, you go that way. We'll all be good." Okay? So one attempts to go that way. The other one keeps going and goes that way. Okay. So I'm going to number these bulbs. I'm going to label this bulb A, so I'm going to label them. I'm going to label this bulb B. Based on the way I've drawn this circuit, is this an all or nothing circuit?
No.
It's not. Notice in my previous one, hang on, I'll come back. All or nothing. If that switch is off, this circuit doesn't operate. That's not the same with a parallel circuit. Okay? In a parallel circuit, you can have branches that are off and other branches that are on. Okay? And so in one circuit, you can have multiple things happening. Which branch, A or B, which light bulb, A or B, would be on in this diagram? Gabby?
B.
B would be on. Why?
Because the switch is closed.
Right, the switch is closed. So we would say this is closed, this is open, and when you have an open switch, you have no electricity. This guy gets here and it's a dead end. He has nowhere to go. He can't get back to the battery. And so, in theory, there will be no electricity running through this branch. I should complete that because it looks a little... Whereas here, it's closed, so it's going over, through, and then it can go back around. And so it can complete that part of the circuit. The electricity always has to leave one end of the battery and return to the other end of the battery. It can never go back to the same end it left. Parker.
Does the electricity on the open one, does it like stop or does it get backed up and then get over?
No, if there is no complete path, it just goes around it. It's kind of like a detour. If there's a break in the road, you don't go there and sit and wait for months until they complete the road and then keep going. Eventually, your GPS tells you, oh, there's a detour ahead, and you just automatically go around the construction. Okay? Colby.
What about with AC current, or is that too advanced?
AC current is totally different, but ultimately, AC current can only still flow if the circuit is closed. If it's open, it won't. But series and parallel works for AC and DC. So if this was an AC power or DC power, this would still work. It just then the current has to be able to go back and forth very quickly. And if it can't pass through that branch, it still won't work. Jaden.
Would there be a way to, like, if you disconnected the battery, could the electricity, like, keep going?
Nope. And with electricity, it's almost pretty much instantaneous. If the battery supply is disconnected, it won't stay in the circuit residually, okay? It'll just be off. If it's connected, it'll be on. There are some things called capacitors. They're a type of electrical component that can keep a circuit powered even if the battery is removed, but only for a very short period of time, okay? Erica.
Why can't the electricity, after it went through line B, go through line A and the
Say what?
other way? After, like,
Oh, I see what you're saying.
why can't
Well, watch. It leaves, finds it has nowhere to go, so it just bypasses it altogether, goes through B, and then you're saying, why can't it go back through here?
Yeah.
Because it has nowhere to go. Electricity has to be able to go, if it's going to go through something, it has to be able to go through and return to the battery, or it'll never even go that route to begin with. So it comes here and it sees, hey, it can sense that there's no way to go through this branch, and so it's going to keep going. It cannot pass through something unless there is a complete circuit.
And then how does
Okay.
that guy turn if he knows that that's not?
He wouldn't, in theory, so we'll just remove him.
But then why did you put the aerial?
The aerial? I'm not familiar with an aerial.
Aerial, Parker.
Please find the definition for me. Is that a mixture between an Oreo and an arrow? Because that would be fascinating. Is it like arrow Oreos?
And they
You
shoot
like
me
open
shooting
your
out your
mouth, they
mouth.
shoot
Oh.
right out your mouth, just-
Fantastic. All right.
Except for the air goes down your throat.
So,
Pretty good.
shh. Where this was all or nothing, this is going to be one or the other or both. Basically, wherever there is a closed branch, the electricity can flow through that branch. Why are parallel circuits more useful than series circuits? Colby.
Because you can run multiple things off of it. Like you can have one thing off while the other thing's on, rather than having both off and both on.
Right, exactly. I can decide which things I want on and which things I want off with just one power supply. So I want you to think about this for a second. Your house,
You have to draw this.
Is our house
No.
a parallel circuit?
your house has one and only one, comes down to a meter and goes into your house, has only one and only one power supply, and it's 120 volts. So when the power comes into your house and then goes into the basement or to the breaker box in the wherever your breaker box is, maybe not the basement, it's providing one source of electricity. So you have multiple circuits, and usually your house is one big parallel circuit. Why would making a house a series circuit not be a good idea? Okay, Colby.
Because if you wanted one thing off, you'd have to shut off everything else.
Right. I go to shut the light switch off. Television goes off. The furnace goes off. The washer and dryer are off. Okay. I turn one switch on and everything comes on. Television's on. The vacuum is on if it's plugged in. All the lights in the house come on. Okay. All the appliances come on.
Everything just explodes.
Okay. Yeah, your house. Little.
And it's off.
You're lost.
Oh,
You're
no.
starting to get your
Series
snuff
circuit.
there.
And then it's go.
Oh no.
It's a automatic car.
It blows up. Okay. So in.
a tree.
So. 5, 4, 3, 2, 1. Your home is a parallel circuit so that you can have multiple branches you can turn on and off. That's especially how if you have light switches that control, multiple light switches that control one light bulb, or if you have different rooms that have their own light switch, okay? You might have all the lights on the one floor of your house might be on one circuit, but you can turn individual lights on and off because they're in branches like this. So your house is wired in parallel. Series circuits are really only for very simple, okay, circuits. Each branch is kind of like having a little series circuit, but then you're connecting them. One last thing. With a parallel circuit, you can have a lot of things, okay? So, real quick, I can have, you don't need to draw this, okay? I could have a lot of light bulbs all in a row. What's the benefit of having, so when a light bulb burns out and there's no switch, it kills the electricity to that branch. Why would this be useful? Why would wiring in parallel be good for Christmas lights? Savannah.
Because if one of your itty bitty little light bulbs go out, the whole thing goes out, and then you have to take them all out and then replace them all because you don't know which one's good.
Right, so is that parallel or series?
That's series.
Right,
That's an
series. So the old light bulbs, this was really frustrating, right? She's exactly right. One light bulb would go, and then you sit there testing each one, pulling them out, checking the wires, putting them back in. It was terrible. But now lights are made where if one light bulb goes out, then the whole strand stays lit except for that one bulb, and you can quickly just change that one bulb out. Okay? So, light, like Christmas lights,
Sherlock.
are now lit in parallel so that it saves us lots and lots of pain. So, like, yeah, look here. That light bulb is out. my whole strand is not dead.
Because there's a bunch of wires.
Okay. All right, ladies and gentlemen, here's what's going to happen. I forgot to copy off your review. I will deliver it to you today before you leave. Your quiz is Friday. Okay? You, however, can still look at the review on bclassroom.com. Have a wonderful day.
Wait,
Just to be